Hey everyone, welcome back to Calculus 2. This is going to be lecture 23 of the course, and in this lecture we're going to start kind of the final section of Calc 2, and that's going to be sequences, series, and convergence. So we're going to be discussing sequences today and kind of getting some of the things defined, like what do we mean by a sequence, what do we mean by a series, and what the heck is convergence. And so this is going to be quite different from what we've discussed so far, though we will definitely make use of the previous material, of course, but we're going to shift our focus considerably here. All right, so let's go ahead and get started. And we'll call this section 4.1, sequences, series, and convergence. Okay. So I think, some of this stuff we've talked about, series, a little bit about series. Well, actually, we've talked about summation notation. We haven't really gotten into series. So maybe this is all new. But let's go ahead and start by just making, cranking out some definitions and getting comfortable with some notation. So the first thing we want to talk about is what's called a sequence. So a sequence, okay, is defined as a function, and there's different ways to define it, but here's how we're going to define it. It's defined as a function whose domain is the set of positive integers. Okay. Now we say the positive integers, but we frequently mean the natural numbers actually here. It's common to represent series. If you're talking about just a generic series, it's common to represent them as A1, A2, A3, right? Dot 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 AN somewhere, dot dot dot, so on, right? So this is a kind of common way to represent, just a generic sequence. There's also, here's an example of a sequence. So this would be just the generic notation, but here's a specific example of a sequence. Maybe A1 is equal to 1 over 1. A2 is equal to 1 over 2. A3 is equal to 1 over 3. And so on. So that means AN would be 1 over N, right, etc. Okay, so you could say an example of a sequence would be 1, 1/2, 1/3, 1/4, and so on, up to 1 over N, and continuing onward. Okay, so this is just a simple example. So this is the definition of a sequence. This is how we generically represent sequences, just some character A in this case with subscripts, right? And here's an example of a sequence: 1, 1/2, 1/3, 1/4, up to 1 over N. Now, if we want to represent the entire sequence kind of in a more compact way, there are different ways to do it. One way to do it is to use brackets with the sequence inside of it, like the A of N. Right. Another way to do it, you might see, would be, actually putting on the indices here. So A of N, the sequence A of N, where N is equal to 1 to infinity. I've seen that also. Sometimes, occasionally, you'll see just A of N inside parentheses without the brackets, right? So these are just different ways to denote the same thing. And I guess, of course, A of N like this with the notation on the outside as well. All right, so we're going to probably tend towards using this notation, right, to denote our sequence, right? And so our previous example could be written like this. So we would say, A of N, the sequence, is equal to 1 over N. Okay. All right. Another example could be, this sequence, maybe 3 plus -1 to the nth power. Okay. What are the terms of this sequence? Well, when n is equal to 1, this is 3 plus negative 1, so it's 2. When n is 2, this is 3 plus negative 1 squared, so it's 4. Right? And when it's 3, it kind of goes back to 2, right? So this is a sequence that just kind of oscillates between 2 and 4 forever. All right. Okay, so that's just an example. Let's see another example of a sequence. What about this one? Let's call it Bn. Maybe n divided by 1 minus 2n. This is another sequence. What are the terms of this sequence, the first couple of terms? Well, when n is 1, you've got 1 over 1 minus 2 times 1. And then when n is 2, it's 2 over 1 minus 2 times 2. And then 3 over 1 minus 2 times 3. 4 over 1 minus 2 times 4, etc. All right, and what do these amount to? Well, this first one is negative 1. Second one is negative 2/3. And then it's negative 3/5. And then this guy here is negative 4/7. Okay, and so on. So you can see here that the numerators are negative 1, negative 2, negative 3, negative 4. Obviously, you can see they're just increasing, right? It's just n. And the denominators are odd numbers, basically. Actually, the negative is coming from the denominator. So it's be like negative 1, negative 3, negative 5, negative 7. I just wrote them with the negative in the up top, but probably a better way to write it would be to keep the negatives in the bottom, just so you can see exactly what pieces are coming from where. All right, so that's another example of a sequence. All right, so let's see what's next here. How about one more example? So let's say our sequence is n squared over 2 to the n minus 1. All right, what does this one look like? Well, you've got 1 squared over 2 to the first power minus 1. Then you have 2 squared over 2 to the second power minus 1. And then 3 squared over 2 cubed minus 1. And so on, right? Okay, so what are all of these numbers? What do these amount to? Well, this is 1 over 1. And this is 4 over 4 minus 1, so 4 over 3. And this will be 9/7. And this one will be 4 squared is 16. 2 to the 4th is 16, and then minus 1 is 15, right? So it kind of looks like that. Okay. So these are all examples of sequences. Now, in and of themselves, sequences are kind of, this is seemingly just a list of numbers, but they're all this list of numbers is all based on some kind of a function. And where this gets really interesting is when we talk about what happens to these sequences as n grows very large. So as n, these are all infinite sequences of numbers, and so what happens to the sequence, to the terms of the sequence, successive terms if you like, as n gets really large. So that's kind of the more interesting thing about this, right? So what happens to the terms of these sequences when n gets really large? Or better said, i.e. when n goes to infinity, right? So this is calculus class. Every math concept that we'll look at has to do with infinity. That's sort of the defining characteristic of of calculus. So what happens to these things as n goes to infinity? All right, what happens to the sequence, to the terms of the sequence very far out? Okay, so what this is basically this kind of question boils down to is what happens in the limit, right? So the limit of a sequence. So really the focus of this section is going to be on sequences whose terms approach limiting values. Okay, so sequences whose terms approach limiting values are said to converge. Okay, so the terms converge if the sequence approaches some definite finite limit. Okay, so for example, the sequence 1 over 2 to the nth power, right? And you can imagine what that sequence looks like, right? It would be, 1 over 2, 1 over 2 squared, 1 over 2 cubed, etc. 2 to the first, 2 squared, 2 times 2 is 4 times 2 is 8, 2 to the fourth, 16, etc. So this is an example of a sequence that converges, right? And so you might just look at these and be able to intuit that, oh, it looks like these ratios are getting smaller, right? The numerator is always 1. The denominator is increasing, right? Pretty dramatically. It's doubling, in fact, every time. And so this is going to be a sequence that you might be able to, infer what the limit is. So what do you think happens as n gets enormous? This would be 2 to like the 10 millionth power, right? It's going to be just 1 divided by some humongous number. And so this sequence actually converges to 0, right? So 1 over 2 to the n goes to 0 as n goes to infinity. This would be kind of an introductory example because it's intuitive that these terms are all getting smaller and smaller, right? And so they are converging to a value, and that value is 0. Okay. Perfect. So that's kind of a very intuitive, sort of a less rigorous definition. But let's define limit of a sequence with a bit more rigor. Okay, so let's go ahead and define that. So let L be a real number. Okay, so real number limit here. Okay, the limit of a sequence, and we'll call the sequence AN. So the limit of a sequence AN is L if for each epsilon greater than 0, there exists an M, capital M, greater than 0, such that the absolute value of a to the n minus L is less than epsilon whenever n is greater than m, little n is greater than m. Okay, so the way we would denote this is kind of the usual way. We would say the limit as n goes to infinity of a to the n, a of n is equal to L. Okay, so L is a real number. Then the limit of a sequence, a of n, is L if for each epsilon greater than 0 there exists some m, this is tend to be a natural number or a positive integer, such that the difference between a of n minus L is less than epsilon whenever n is greater than m. Okay, sequences that have limits, as we already said, but we'll write it down here. Sequences that have a limit converge. That's what the terminology we use. We say a sequence converges if it has a limit, and if it sequences that do not have a limit are said to diverge. right? So you either converge or you diverge, one of the two. If you have a limit, then you converge, otherwise you do not. Okay, all right, so what does this mean? All right, well, let's draw a picture first and see if we can reason a bit about this definition with a picture. Okay, and so pictures are always just as good as I can draw them, but let's say we've got some limit. So this is a sequence, and so I'm gonna just be interested in the integer domain here, right? So this is your x, right? But these are all just integers. So 1, 2, 3, 4, 5, 6, 7. You can think of this as, you know, kind of like a function, but it's all discrete, right? There's no nothing in between the integers is important in the sequence, right? So let's say maybe when n is equal to 1, the value of the sequence is way up here. Don't worry about what these values are. That's not important. And let's say when n is 2, the value of the sequence is down here, right? Then when n is 3, it's here. When n is 4, it's there. And when n is 5, right? So you can kind of see what's happening here. Right, so the terms are kind of coming closer together, right? So when n is 7, maybe it's up here, and then at 8, you know, and then at 9, right? So it kind of does this, right? So I'll just put this on here. This just kind of shows you the order of the terms. Okay, so the sequence maybe does something like this. It starts out with the terms very far apart on the y-axis here, and then as n grows, they tend to kind of come together. Okay, now what this definition is that, you know, we're basically going to say, okay, here's our limit L. This is what we say that the terms are all tending towards. So let me just draw this in here. All right, so that's L. Now what the definition states is, you know, the limit exists if for any epsilon greater than 0, and all we mean by that is just any positive number. Now typically epsilon is taken to be a really small number, like, you know, 0.00000, some really small number, right? I mean, this is the interesting case anyways. I mean, epsilon could be anything, but when epsilon is really, really small, then what this definition is saying is that for any epsilon, no matter how small you like, there's going to exist some value of m such that whenever n is larger than m, the sequence is going to be within epsilon of the limit. And so that's exactly what we see here, right? So let's say that our epsilon is some value, and so this would be L minus epsilon here, and this would be L plus epsilon here. Right, so this is not a terribly tight interval, right? But what you can see is that the way we've drawn this is that once n is equal to 6, or sorry, if we set big M equal to 6, then for all n larger than big M, right, namely all of these values in the sequence is within epsilon of this limit. Right now, so what you can imagine is if I shrink this down to a very tight interval, right, then I have to go further out. Right now, in order to get it even tighter, I have to go further out. I have to go out to at least, you know, n equals 8, or sorry, m equals 8. Right, and I can continue to shrink this down until epsilon is so small that I have to go out to like m equals 10 million or something, right? But then once I'm out past m equals 10 million or n equals 10 million, then all of the values of the sequence beyond that will be within epsilon of the limit. Okay, so that's the idea. Just basically, the idea with a limit or a converging sequence is that the terms get closer and closer together as n grows. Right, so kind of like in this picture, you can see that they kind of do this. Until if you were way out here, you know, at n equals 1,000,000, the naked eye wouldn't be able to perceive on a visualization like this that the dots were, you know, not in a straight line, right? But if you were to zoom in, you'd see, oh, indeed, there is some fluctuation, right? But it's so small that it's practically non-existent. That's the idea with a convergent sequence. The terms get closer and closer together, as n grows. Right? And so that's why we say that the sequence goes to the limit L as n goes to infinity. Right? So out here at the beginning, the terms are not even close to L, but as we go further into the sequence, we see that in fact the terms tend to get closer and closer to L. Okay, so the next, so the nth term is certain distance from L, n plus 1 term is closer, n plus 2 term is even closer, n plus 3 term is even closer until there's practically speaking no difference between the two. Okay, that's always very subjective, depending on your resolution. If you're looking very closely, they may look very different, but that's what we mean by for all epsilon. No matter how close you want to be to L, you can always go out and find an M that gets you that close. Okay. Okay, so as I said, in practice, these epsilons will be very small. That's like where it gets interesting, is when epsilon is very, very small and m greater than 0 will be very large. So I think a lot of times instructors don't point this out, and it kind of gets lost, right? But this is the key, right? Is that if we want to be very, 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 very close to the limit, to L, if we want the terms of our sequence to be very, 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 very close to L, then epsilon has to be tiny. It has to be infinitesimal. And that is going to necessitate that we go very far out onto the sequence before that is realized. Okay. Now the beauty of this definition, of course, is that it says for any epsilon greater than 0. So that just means that you can make it as small as you want, which basically means they're infinitely close. Okay. So, well, we don't say infinitely close. We say arbitrarily close. Okay. All right, perfect. Perfect. Okay, so that's the idea of, that's the definition of a limit, right? We'll use this in places, but kind of like what we talked about when we were discussing limits, in Calculus 1. There is a specific course in a math curriculum. It's usually called real analysis or functions of a real variable, that kind of stuff. But that's the course where this definition gets explored and fleshed out in lots of detail, right? So in calculus, we're a little more focused on the results and kind of setting the stage for higher mathematics. So we aren't going to use this nearly as much as you would in that analysis course, which I highly recommend people take. If you find this stuff interesting, you will absolutely love real analysis. It's one of the best courses. It's one of the by far best undergraduate math course you can take. It'll also leave you in a much better. You'll learn so much. You'll have your reasoning abilities and just the way you think about mathematics. Your sort of mathematical maturity will be leveled up big time by that course. So, okay, all right. So let's start discussing some properties here. So the first one is the following. This is more of a theorem. So this is the limit of a sequence. Okay. So let L be a real number. Let F be a function of a real variable, okay, such that the limit as x approaches infinity of f of x is equal to L. Okay, so L is a real number, f is some function, right? So seemingly we're back in calculus 1. So f is a function of a real variable that has a limit as x goes to infinity. Right? As x grows, the function approaches this value L. Well, if a of n is a sequence such that f of n equals a of n, and I should say for every n, then, you know, the limit as n goes to infinity of a of n will also equal L. Okay, so this is, you know, in some ways this is totally obvious, but I think it's something that does require, you do have to say it, right, before you will just accept it. But basically what this is saying is that, hey, look, if I have a function, f, and it's got a limit as x approaches infinity, right, if it has some limit, that it, you know, there's a limit for this function, then, look, I can just evaluate f at all of the integer values, right? If x, you know, obviously if this limit exists as x goes to infinity, f is going to be defined for all positive integers, right? It's just also defined for all of the numbers in between the integers, right? But I could certainly plug in a 1, I could plug in a 2, I could plug in a 3, I could plug in all of the integer values. And what this theorem is basically saying is that if that's the case, if in fact f of n is equal to a of n for every n, all of the natural numbers n, then the limit of the sequence is equal to L as well. Okay, so I mean basically if a sequence agrees with a function at every natural number and the function has some limit, then the sequence has the same limit. Okay, that's all this is. This is kind of rather sort of obvious, right? But all right, so let's just kind of say it the obvious way. So if a sequence a of n agrees with a function f at every natural number, so 1, 2, 3, 4, 5, 6, all of those natural numbers, and if f of x approaches some limit as x grows to infinity, then obviously f of n is going to approach the same limit, right? If I restrict the domain of f to just the natural numbers, it's going to also approach that same limit, right? And also, that means the sequence is going to approach that same limit, right? If f of n is equal to a of n for all n, then a of n is going to have the same limit as f of n. Okay. All right, perfect. So let's do an example here. So let's say we want to find the limit of the sequence whose nth term is a of n equals 1 plus 1 over n to the nth power. Okay. If you recall, if you're watching these in succession, you may recall that when we discussed L'Hopital's rule, we saw a function that looked just like this. So in the L'Hopital's rule section, we saw that the function f of x equals 1 plus 1 over x to the x power. We saw that this function tended towards e as x grew to infinity. All right, so what we said there, you know, precisely was that the limit as x goes to infinity of 1 plus 1 over x to the x power was equal to e. Right, now this was not a trivial limit to identify. We had to, you know, invoke L'Hopital's rule a couple times. We had to do some algebraic maneuvers, but we were able to show that this was true. Now, what we need to recognize here is that we can apply the previous theorem here. Now, notice that 1 plus 1 over n to the nth power is going to be the same as 1 plus 1 over x to the x power if I restrict the domain of f to just the natural numbers. Right, so for example, right? A of 1, the first term of this sequence, is going to be equal to 1 plus 1 over 1 to the first power, right? And f of 1 is going to be equal to 1 plus 1 over 1 to the first power, right? Just plugging in, right? A of 2 is going to be 1 plus 1 over 2 to the second power. And then, of course, f of 2 will be the same, right? It'll be 1 plus 1/2 squared, right? And so on, right? This continues on. So basically, this sequence agrees with this function at all of the positive integers and natural numbers. So that means that this limit is also going to be the limit of the sequence. Okay? Right? So basically what this, this is great, right? This is fantastic because all of the things that we've learned about evaluating limits thus far can be directly ported over to our discussions of sequences, right? So anything that's true of a function, where x is any real number, limit-wise, ought to be true also of sequences, where we just restrict the domain to natural numbers instead of making them all real numbers. Okay, perfect, right? So this is great. This is why we just kind of lead off with this theorem, because automatically this gets us a ton of all of the stuff we developed in Calculus 1 now applies here, and all of the stuff that we've looked at in Calculus 2 related to limits also applies here. So big gain there. Okay, perfect. Now let's talk about some other properties of limits of sequences. So we'll let the limit of a of n equal L and the limit of b of n equal k, right? So I got two limits. I got two sequences, separate sequences. I got a of n and b of n, right? They both have limits. They're different, though. Well, they could be the same, but not generally, not necessarily, right? So L and K. Okay, so if that's the case, then what can we say here? Well, all of the conveniences that you would expect are going to emerge here. So a of n plus or minus b of n, that limit. So if I take the terms of a and b and I add them, a1 to b1, a2 to b2, a3 to b3, or I subtract them, then it's the same as subtracting or adding the limits. Okay, so that's nice, right? That's very nice. It's also true that if I multiply the terms of the limit by a constant value, so c times a of n, we'll say, then that's going to be equal to c times the limit. Right, so if there's some sequence that has a constant attached to it, you can pull that constant out of the terms, evaluate, the sequence with just the a of n part of it without the constant attached, and then identify the limit and then just multiply by the constant. Right, so in a lot of cases that's very convenient, and this is obviously for any c that's a real number. So any constant real number. Okay, same thing is true for products. So the limit of a of n times b of n is equal to L times k. Very nice. And finally, ratios, right? The limit of a of n over b of n ought to be equal to L over k. Now the assumption here is that bn is non-zero, right, for all the terms of the b sequence. Okay, but that's they don't get nicer than this, right? So all of the things that you would hope are true of sequences are true of sequences. Okay, so you can add or subtract them, and the limits add or subtract. You can multiply by a constant, and the limit multiplies by a constant. You can multiply them or divide them, and the limits are multiplied or divided. So this allows us to kind of break sequences apart really conveniently, add them together, divide them down, factor all the stuff that we like without losing the structure and keeping with retaining all of the properties of the limits. So that's very nice. That's very nice. Okay, let's do some examples where we just kind of try to figure out what the limits are, if there is one. Let's start with a simple one. Let's consider the sequence a of n equals 3 plus negative 1 to the nth power. So what about this guy? We saw this one. This is one of our introductory examples. Right, so we said there that, you know, the sequence was, what were the terms? The early terms? Well, it was 2, and then 4, and then 2, and then 4, and so on, right? So, you know, clearly there are only 2 values in this sequence, and they oscillate back and forth between one and the other. So it's 2, and then it's 4, then it's 2, then it's 4, then it's 2, then it's 4. Does this sequence converge? No, right? Definitely not. This sequence doesn't ever change. It stays exactly the same. So, I mean, we'll just say clearly a of n does not converge. Right? Because the terms never get closer to one another, right? This would fail the for all epsilon greater than 0, right? It would be easy for me to come up with an epsilon for which the terms are never successively that close to one another. Like if I just say epsilon equals 1/2, right? There's no n. If I go out farther and farther on this sequence, these terms are never within 1/2 of each other. They're always separated by 2, right? Okay. Perfect. So that's the first example. This one does not converge. What about, let's consider the sequence b of n equals n over 1 minus 2n. This is a more interesting sequence. All right, so remember what this one looked like. We had 1 over negative 1, and then 2 over 1 minus 4, so negative 3, and then 3 over 1 minus 6, so negative 5, and we can see the pattern here. Okay, so all these values are negative. The question is, are they getting do they get arbitrarily close to some other value as n grows? So let's just think of this as a function and kind of go after it. So let's say limit as n approaches infinity of n over 1 minus 2n. Well, let's divide the top and bottom by n. So if I say n over n up top, and then down below, let's divide everything by n. I can certainly do that, right? I can do that. 1 over n minus 2n over n. Right, so then I have the limit as n goes to infinity of 1 over, now what do I have down here? I've got 1 over n minus 2, right? Okay, now what happens as n gets large here? Well, this piece goes to 0, right? Right, but I'm still left with what? Negative 1/2. So I've got the 1 over negative 2. So 0 minus 2 is negative 2 on the bottom. So this piece is going to become, as we go further and further out, as n gets larger and larger, this piece gets closer and closer to 0, and you can begin to treat it like 0 at a certain point. It's so small. Right, so this one has a limit of negative 1/2. So b of n goes to negative 1/2 as n goes to infinity. Perfect. So this is an example of a convergent sequence. All right. Very good. Let's see what's next. How about this example? This series does converge. Our sequence does converge. Let's show it. Let's show that a of n equals n squared over 2 to the n minus 1 converges. Okay, so we know it converges. We're told it's convergent, that it converges. let's see what we can do with this. Let's just kind of think of this as a function. F of x equals x squared over 2 to the x minus 1. All right, so we have to kind of think of this as a function because you can look at this and you can say, well, if I try to just directly input infinity into this expression, if I kind of naively attempt that, then this is going to produce, well, let me write it first. The limit as x goes to infinity of x squared over 2 to the x minus 1. This is going to produce infinity over infinity, right? So this is going to be a case where we're going to use L'Hopital's rule to try to find a limit of the function, and then we're going to fall back on the fact that the sequence is the same as the function at all the integer values, positive integer values. So this produces infinity over infinity. So let's differentiate, right? So this limit would be the same as the limit as x goes to infinity of the derivative of x squared divided by the derivative of 2 to the x minus 1. And so the derivative of x squared is 2x, and the derivative of 2 to the x minus 1, which you may or may not remember, is the natural log of 2 times 2 to the x. Okay, now what happens here? Well, here again we have, infinity over infinity, indeterminate form, right? Okay, so let's differentiate one more time, because if we differentiate one more time, then this will just be a 2. So the limit as x approaches infinity of 2 over, now what happens here? This is the natural log of 2 again, so we'll just say squared times 2 to the x power. Now what is this limit? Well, this is 2 over the natural log of 2 squared, so that's some constant, but it's all being divided by, but this thing is being divided by 2 to the x, which is going to grow without bound. So this is equal to 0. Okay, so let's recap, because the chain of implication here is important. Okay, so what did we do here? Well, we started with this sequence, and we said, all right, we're going to use the fact that this sequence is going to be the same as this function at all integer values, right? So we're going to use this as our proxy. And the reason we need to consider this as a function is because we got to take derivatives, right? And so we looked at this and said, oh, negative, we got this, we've got this indeterminate form here. So because we're thinking of this as a function, we can calculate the derivative, right? 2 to the x over ln 2 to the x, 2 times x over ln 2 to the x, right? But here again, we've got this indeterminate form, so we can differentiate a second time, right? And so once we do that, we see that this is equal to 0, right? So the fact that this limit exists means that it's equal to this limit, which means that it's equal to that limit, which means that the sequence is going to converge to the same limit. Okay, so the implication here is that a of n goes to 0 as n goes to infinity. Okay, now hopefully that is reasonable here, right? It would make sense if you kind of look at this. It should make sense, hopefully it does, that this numerator is going to grow pretty fast, right? N is being squared successively, but this denominator is going to grow quite a bit faster, right? Because as n grows, we're increasing the exponent here, right? So the top will be 3 squared, this will be 2 to the 3rd power. Once we get to 4, this is 4 squared, and then it becomes 2 to the 4th power, and then it's 5 squared and 2 to the 5th power. And so this denominator is going to overtake the numerator at a certain point. So, very good. And so you can kind of think to yourself, if you just kind of crank out a couple of examples of n squared compared to 2 over n, or 2 to the n power, you'll see that, oh, indeed, this denominator is going to grow much faster, especially as n gets larger. Then it starts to really overtake it like crazy. So, very good. All right. Good example. Okay. Now, we're going to need some additional notation, so I'm just going to introduce this here. Many of you will be familiar with this already, but some will not. So the factorial notation. Okay, so a lot of some of the upcoming formulas and examples we'll see will be greatly simplified by thinking of factorial notation, by using factorial notation. So some people may have seen this. When we say n factorial, we kind of write it like this, n with an exclamation point, factorial. This is literally read n factorial. Okay, and what does n factorial equal? Well, it equals 1 times 2 times 3 times ... times n. Basically just multiplying all of the value, all of the positive integers less than and equal to n together. Right? So for example, 5 factorial is 1 times 2 times 3 times 4 times 5. 4 factorial is 1 times 2 times 3 times 4. 3 factorial, 1 times 2 times 3. Right? Now what about, well, let's do them all. 2 factorial is 1 times 2. What about 0, or 1 factorial is 1? What about 0 factorial? That's the weird one. Well, 0 factorial is defined as 1. Even though it's a little bit strange. It's defined as 1. Okay, so that's the factorial notation. Now we have to be a little bit careful with factorials, right? So for example, if you see something like this, when it's written like that, what does that mean? Well, what that means is 2 times 1 times 2 times 3 times ... times n. Right, that's what that means. What does it mean if I write it like this? Well, that means something different. That means 1 times 2 times 3 times ... times 2n. Okay, so obviously totally different, right? So you have to be careful. It's kind of like, you know, if you have 2x squared versus 2x squared. They mean different things, don't they? In this case, just the x is squared, whereas here you're squaring 2x each time. Well, that's kind of the same thing here, right? If I have the 2 out front without the parentheses, then the n is assumed to be the factorial part of it, whereas if I have the parentheses, then it's 2n, right? So very different. Okay. And some of the other stuff that we'll see with factorials, and this is just an aside, but ratios of factorials you have to be a little bit careful of, right? So for example, if I have 3 factorial over 5 factorial, right? What is that? Well, let's say 3 factorial over 6 factorial. Right. Well, what that literally means is 1 times 2 times 3 over 1 times 2 times 3 times 4 times 5 times 6. Right, so some of these will cancel away, and you'll see that you have 1 over 4 times 5 times 6. Right, so the cancellation is, you know, is somewhat different than what you might expect. This is not the same. So 3 factorial over 6 factorial does not equal, you know, 1 factorial over 2 factorial. Okay, so you just have to be careful of that. Like that's, you know, if you're not used to this notation, you have to be cautious, right? This is not true. Okay, so you might, you know, if these were just integers, 3 and 6, you would say this is 1/2, but it isn't true that it's 1 factorial over 2 factorial. Right? This is in fact what happens here. Okay, so you just have to be a little bit careful with this factorial stuff. Some of you will have seen this. Honestly, you might see it in like a pre-calculus course, I guess, maybe in Algebra 2 or something like that. But it could be new to many people. So I just like to point it out because it'll come up in some of the expressions, some of the sequences we're looking at will consist of this. Okay, perfect. All right, now back to sequences. Let's take a look at a theorem. And this is really, I guess, what you would kind of call what you think of as the squeeze theorem for sequences. Okay, so the squeeze theorem for sequences. I'll just write that. So we recall the squeeze theorem. I believe in Calculus 1 we talked about, two functions have the same limit, and there's a third function that's always bounded by the other two, then the third function will have the same limit as well. It's an identical idea here, but just for sequences. So if a of n is a sequence with a limit, I should write limit. So if the limit of a of n is equal to L, and that is the same as the limit of another sequence, b of n. So if you have these two sequences, a of n and b of n, and they both have the same limit L, and if there exists an integer n, okay, such that a of n and b of n are kind of bounds on the value of some other sequence terms, c of n, and this is true for all n greater than n. Okay, well then the limit of c of n is equal to L as well. Right, so if a of n and b of n have the same limit, and if there's this third sequence c of n such that once you get far enough out on the natural numbers or the positive integers, then all of the a terms are smaller than c and all of the b terms are larger than c, right? If this holds for all n greater than some value of n, some integer, then the third sequence will have the same limit, right? So the third sequence is going to have the same limit if this is true. Now let's see an example. Hopefully this is well, let's draw a picture first. Let's draw a nice picture of what this looks like. Okay, so let's say I have my a of n sequence here, and let's say also I have my b of n sequence. Right, they kind of look like this. Now I've just drawn this as a line, but remember these are just discrete points because these are sequences. Right? But the idea is that these sequences get closer and closer together and they have the same limit L. Right? Now if I have some third sequence, some Cn sequence, which is maybe crazier, maybe it starts out down here and then it comes up to here, it kind of goes like this, and then it bounces back down and then it comes back up. But then eventually it settles down between a of n and b of n, right? So here's my c of n sequence. If that's the case, right, if this kind of behavior can be shown of c of n relative to a n and b of n, then clearly c of n is headed towards the same limit, right? So a of n goes to L, b of n also goes to L, and a of n is less than c of n less than b of n. We say less than or equal to, I suppose. Then c of n goes to L as well. Right, so this is hopefully a simple idea. All right, hopefully it's so. Yeah, hopefully. I mean, when you see a picture like this, like, oh yeah, that's kind of obviously true, right? And sometimes when you're reading a description like this, maybe it isn't obvious, like what the heck is being said, but then translate it into a picture, right? Or maybe the picture looks slightly different, right? Maybe it's limits don't always look like that. Maybe what happens is you've got something that goes like this. Maybe this is your b of n. And then you've got, an a of n that kind of comes like this. And then maybe your c of n starts out really high, but then comes down into this range. Could look like something like that. Right? So as long as at some point the terms of c are between a and b, and that holds forever beyond a certain point, namely n, then the three will have the same limit. Okay? So that's the idea with the squeeze theorem for sequences. So really convenient, just like we saw, like this can be convenient if C is really hard to look at or analyze or has a strange expression. But if you can show that it has a relationship between A and B and A have the same limit, then you can frequently derive the value of a limit for C using this theorem. Let's do an example like that. Okay, let's show that -1 to the nth power times 1 over n factorial converges. Okay, let's take a look at this one. All right, so this is an example of a sequence that's not very great to look at. Okay, so let's consider two other sequences. So let's consider A of n, and we'll denote that as -1 over 2 to the nth power. And let's consider B of n, the sequence 1 over 2 to the nth power. Okay, now both of these converge to 0, right? That's probably something we can just see, right? But this would be like -1/2, -1/4, -1/8, and so on. Obviously, terms are getting closer and closer to 0, but from the negative side, B of n will be, you know, the same thing except positive. Right, so you can kind of think of these two, and so your A of n is kind of going like this, B of n is kind of going like that, right? And they're sort of coming together here at y = 0. Well, y = 0. At 0, the value of 0. We should say y = 0. These aren't functions; they're sequences. So, so what does C of n look like? Okay, let's actually write some of these terms out here. I think this will be instructive. So A of n, the terms here, we just kind of wrote some of them. I'll just rewrite them. -1/2, -1/4, -1/8, -1/16, -1/32, right, and so on. Right, just doubling every time. What does Bn look like? Let's put Bn down here. Actually, probably should have put Bn on top, but that's okay. So this is 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, right? And, you know, remember, these are going to go on forever, right? These are just the first couple. And then let's look at Cn. What is Cn in the middle here? Well, Cn is going to be, you know, it's going to be positive or negative depending on n. So when n is 1, it's negative. When n is 2, it's positive. So it kind of oscillates. Well, let's see what this looks like here. So the first term would be -1. Right? So you can see that would be -1 times 1 over 1 factorial. Okay, then the second term would be 1 over 2 factorial, would be 1 times 2, so it would be 1/2. And then it's going to be -1 over 3 factorial. And so that's going to be 2 times 3, 1 times 2 times 3, which would be -1/6. And then it's positive 1 over 24, right? So 4 factorial would be 1 times 2 times 3 times 4. So it would be 6 times 4 is 24. And then you've got 1 over 120, and then 1 over 720, and so on. Okay, so notice here, the first term, you know, C of n is outside of the range of an to bn. So C of n is way, you know, it's way, if you think of it like this, it's -1, so it's like way down here, right? Whereas your A of n is -1/2, so it's outside. And then when we move to the second term of the C series, of the C sequence, we have 1/2, which is also outside. So the second term is up here. All right, so it kind of goes like this. And then it's going to be 1/6, so it's still outside. right? But then notice what happens here. Here's where the changeover occurs. Right now, 1 over 24 is definitely between these two. And look at the next term, 1 over 120 is definitely between these two. Right? So you can kind of think of it, these numbers are very close to 0. They're closer to 0 than these numbers are. Right? And so what's going to happen here in the picture is it kind of comes up like this, and then it stays between these two forever. Right? Now to really kind of see that it stays between these two forever is a little bit more involved. It's a little bit trickier. What we would have to do is kind of we'd have to look closely at n factorial versus 2 to the n. But what we'll find, if you do that exercise, you'll find that n factorial is greater than 2 to the n for all n greater than 4, right? Just what we see here, right? It goes from 1, 2, 6, 24, and then after that, these are the 2 to the n's, and here's n factorial, right? So much, much larger. Which means that 1 over that number is much, much closer to 0. Okay, and so so this is kind of a side project that you can take on yourself. Kind of break this down. Maybe look at a bunch of values, or maybe think about what does n factorial mean relative to 2 to the n. Right? They mean similar thing. Well, we can just to kind of give you a hint on how to think about this. So n factorial versus 2 to the n. Let's just say n equals 10. So over here, this is, what does n mean? It means 2 times 2 times 2 times 2, 10 times, right? What does it mean over here? It means 1 times 2 times 3 times 4 times 10, right? 10 things in this product, 10 things in this product, right? Over here, all the things are 2. Over here, all the things are greater than 2 except for these two, right? So you can see you're just multiplying larger numbers together. And this disparity is going to become increasingly significant as n gets really big, right? If n is like 10,000, I'm going to be multiplying 10,000 2's together. Whereas with n factorial, it'll be 1 times 2 times 3 times blah, 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 times 9,999 times 10,000, right? So much, much larger. All right, so you can kind of explore this. And I think probably just with what I've said here, you can see that n factorial is way bigger than 2 to the n for large n. But yeah, maybe there's other ways to think about it. So side project. But basically, what does this tell us? Well, we can see that, what we just saw was that negative 1 over 2 to the n is less than or equal to negative 1 to the nth power over 1 times 1 divided by n factorial, which is less than or equal to 1 over 2 to the n, right? Whenever n is greater than 4, right? So basically, this is the condition that the C sequence has to have relative to the A and B sequence in order for the squeeze theorem to be true. And so we know that the limit of A of n is equal to the limit of B of n, which we said was 0. And so that implies that the limit of C of n equals 0 as well. All right, perfect. Okay, let's go ahead, and we've got more to talk about. This is a very long section, so I'm going to pause the video here, and we'll end the video here, and we'll have a part 2 to this video. So we'll be back in a moment with part 2.